Welcome to Lecture 6 for Chemistry 141, and we're going to look at the start of quantum mechanics and really how it all began with light. So you can kind of look at the birth of quantum mechanics just in general, and if we really look back at the early 20th century, so the early 1900s, chemistry really evolved as far as our understanding of the atom. And if we look at the names on the equations and the names of the people who were involved with creating our understanding of the atom for the time, they really do represent some of history's most brilliant minds. And it's one of those times in history where a lot of important people found each other and were able to get together and work out some of our more complex mathematical problems and how they applied to quantum mechanics. So a lot of these concepts were extremely difficult to comprehend, some of which we still try to understand today. You may see some of that in the news occasionally where they're looking at Schrodinger's equation, or if they're looking at some of Einstein's theories, and we still try to understand some of what they came up with almost 100 years ago. So a lot of things we do is still just an approximation as far as quantum mechanics, and we'll talk more about that as we go through this chapter. Well, let's first talk about light. It was discovered that electrons share a lot of characteristics with light. So before we can really start to understand the electrons going around an atom, we really need to understand how light works. And as it turns out, most of our really tiny particles have the same characteristics as light. Now, light is also called electromagnetic radiation. And the reason for that is that it has an electrical field component and a magnetic field component that we see down here in our graph. And we know that light moves very quickly. We hear the term the speed of light very fast. It is a constant that we use quite frequently in this unit. Our speed of light is given to us by the letter c, and it's equal to 3.00 times 10 to the 8th meters per second. If you carry that out to more significant figures, it ends up being 2.998 something something. So we just usually round 3.00 times 10 to the 8th. Let's characterize our light. Light can be characterized three different ways, either by its wavelength or its frequency. And then we'll also sometimes characterize it by its amplitude, which doesn't have a specific Greek letter there. Wavelength is usually given by lambda, and frequency is usually given by the Greek letter nu, not a V as it looks like on the screen there. That is a Greek letter nu. Amplitude doesn't really have its own letter. Let's look at each one of these. So wavelength is the physical distance between crests of a light wave, whereas frequency is the number of crests that passes a point in some given time. Now, these two quantities, wavelength and frequency, are in fact related to each other through c, and we'll see that equation here in just a little bit. Now, amplitude is really the vertical height of your crest of your wave, and that's what determines the intensity of your light. Let's take a look at some cartoons here on these things. So when we're looking at a wavelength here, so here we see a wave of light. We see we've got our wavelength here going from crest here to crest here, and then we've got our amplitude just right here, so the height of that crest right there. And what we don't see here is frequency. If we can imagine that our light wave is moving in that direction, we would count the number of crests that pass, maybe a certain point here in a second, and that would be the frequency and the number of crests per second. Now, if we look at how we characterize light using wavelength in particular, the wavelength of light is what gives us our different colors. We see here we've got a fairly long wavelength out here, and we have a slightly reddish tint, so a long wavelength tends to be red. We have a wavelength here somewhat in the middle, and this is going to be a yellow wavelength. And then we have our really short wavelength here, which tends to be in the blue and violet range. So as we go through the colors, what we're really doing is changing wavelengths. When we change wavelengths, we also change frequencies, because those two things are related. We're going to talk about that in just a moment. Now over here we see for For our amplitudes, as we have dim light, we see our amplitude is just very low here, and for bright light, our amplitude is actually fairly large. And so the larger we make the amplitude, the brighter we would make that light. Now we talked about how wavelength and frequency are related, and it turns out for any object that's in motion, wavelength and frequency are related. However, we don't really worry about any large objects for that. We focus strictly on smaller things like electrons at the biggest, and then down to light particles. But the equation that relates these two guys is c, the speed of light, is equal to the wavelength lambda times the frequency nu. Now, since c is a constant, that has some ramifications about these two values. As lambda increases, nu decreases. So as the wavelength increases, the frequency decreases, okay, and vice versa. So as lambda decreases, frequency increases. So we saw that as we go from red light to yellow light to blue light, our wavelength was decreasing, it was going down, and that means we've got more crests in a certain little area. So that would mean that our frequency would increase in that time. And we'll eventually get to the point where we're relating that back to energy. Let's take a look at an example here. So we have a green light laser that has a wavelength of about 515 nanometers. And we want to know, what is the frequency of this light? Let's go ahead and work that one out. For our green laser is 515 nanometers. And we also know, since we're dealing with light, that we have a speed of light equaling 3.00 times 10 to the 8th meters per second. Okay, so what we're looking for is our frequency for that. Now we do have an equation that relates c, lambda, and nu. So we have c is equal to lambda times nu. Now we're looking for nu, so let's go ahead and rearrange this equation. We're going to divide both sides by lambda to get nu all by itself. That's going to allow my lambda here to cancel, and that leaves me with c over lambda is equal to nu. So it would seem a very straightforward process at this point to just go ahead and take our speed of light, c, divide by our lambda wavelength, and get our nu. The only problem is we have issues with units. Notice my length unit for lambda is in nanometers, and my length unit for the speed of light is in meters. So we're going to have to get those two things to be the same in order to cancel them out. So we're going to have to convert one of those. Let's go ahead and convert our lambda into meters. So we're going to take lambda, so that's going to be equal to 515 nanometers. We're going to multiply that by a conversion factor, and since we want meters, we're going to put 1 meter up on top. And if we look up the conversion factor between meters and nanometers, there are 10 to the 9th nanometers per every meter. So that allows our nanometers here to cancel, and we end up with a lambda of 5.15 times 10 to the minus 7 meters. So now I've got my lambda in terms of meters, I've got my c, so let's go ahead and calculate this out. So I've got 3.00 times 10 to the 8th meters per second over 5.15 times 10 to the minus 7 meters. My meters cancel. The only unit I'm left with is 1 over seconds. It's a weird unit, but that's okay. We're going to see how that comes out. Now this comes out to be 5.83 times 10 to the 14th with units of 1 over second. Turns out 1 over second is in fact a frequency unit, and we give it a more appropriate name, and we see that it has a name of hertz. Now, so far, all we've really been looking at as far as our light and what we generally think of as light is just a very small portion of the electromagnetic spectrum that we interact with as far as our eyes, and that's called visible light. Well, in fact, the electromagnetic spectrum contains lots of different types of light, ranging all the way from radio waves to gamma radiation. We see here we've got radio waves on the low energy side of these. Change color. So we've got radio waves down here at low energy, and we've got things like gamma rays way up here at high energy. And this little tiny section right here is our visible light, just that little area in there. Now it turns out we interact with all these different forms of radiation just in different ways. But let's take a look at each one of these different forms of light. So radio waves, very low energy. Our radio and TV signals are made up of radio waves, so we use those for that. Microwaves, well, we use those in microwave ovens, and microwave radiation is also generally what we use for radar. Infrared radiation is how we interpret heat. So our body picks up infrared radiation and says, "Ooh, that's hot." Visible light there, that's what we use for sight. That's what our eyes interact with. Ultraviolet radiation, that's what we get from the sun. It's what gives us our tans. It's what gives us sunburns. It is required by our bodies to create some of the vitamins and nutrients that we require to live. X-rays, we use X-rays in medicine. X-rays have an energy sufficient to pass through flesh, but it cannot pass through bone, which is why we use it to look at the bones inside of our body. Then we have gamma radiation, which comes from interstellar or atomic decay sources and nuclear sources. Extremely high energy light. Generally, it does not pass through our atmosphere. The Earth's magnetic field tends to steer away most gamma sources. However, every once in a while, a gamma ray does come through, and it generally passes through everything, and including possibly just passing right through the whole Earth itself. So really interesting stuff there. This is a lot more physics stuff than chemistry stuff, but it's good to know what we've got there in the electromagnetic spectrum. Now, one of the more interesting things about light is that it does have what we call a wave-particle duality. So there's some ways where it behaves as a particle, and some ways where it behaves as a wave. Now, the first thing that people notice is that light behaves as a wave, so we'll take a look at that as well. One of the things that people noticed so many years ago is that light can undergo interference. And what this really is the interaction of one light wave with another light wave depending on the relative phase. So we have two types of interference. We have constructive interference, where we have two waves adding to each other. So if we were to add these up, if we had a line going through here and a line going through here, so these two crests would add together because they're overlapping. These two troughs would add together because they're overlapping, and these two crests would add together overlapping. And we end up with really much higher crests and much deeper troughs. So that's constructive interference. Destructive interference is where the waves are out of phase and you have the crest of one overlapping with the trough of another. So if we again take a look at our line here, and we have our up part of the wave here and our down part of the wave here. When those add together, you end up with nothing over here, and you see that all the way through, and so you end up with no light wave left. The two waves have completely canceled each other out, so that is called destructive interference. Now, light also undergoes diffraction, which is the bending of a wave around an obstacle. So if we look at how waves pass through a very thin slit, we see that even straight waves here turn into curved waves here as they pass through. You can kind of imagine as the wave is passing through, they kind of get dragged off those edges there and create those curves. Okay, particle behavior just goes straight through, and doesn't get diffracted at all. So there are some ways in which light behaves as a wave, and some ways in which it behaves as a particle. Now if we look at two-slit diffraction, we get kind of a combining of some of these two things. So here we have a light source. Here we have our light coming through as here they show it bent. It could easily be straight as well. But now that we have two slits, we have two sets of waves setting up now here, and as they start to spread out and they start to come together, we start to see patterns of constructive interference and destructive interference. And on the film where it's at, you start seeing areas of destructive interference here and constructive interference here. So you have really bright and then really dark, and then really bright, bright ones here are in red, and then really dark. So you have these alternating patterns. That was supposed to be a dark one there. So you have dark and light, dark and light. So where the really light spots are, we have constructive interference here, and where the really dark spots are, we have destructive interference. So we start to get what's called a diffraction pattern or an interference pattern. So that's how we know light behaves as a wave. Now what about light as a particle? Well, we looked at light as only a wave for quite some time until certain observations were made. A lot of these by Max Planck and Albert Einstein. And one of these things is the photoelectric effect. And this is where you shine light onto a metal surface, and at some point that metal surface will begin to eject electrons as you change the voltage. So as you change the voltage, or you change the frequency of the light rather. And so as you change the light, when a metal or an electron gets ejected off, it comes across and it hits this tube here, which then connects a circuit going to a battery, and the little current meter says, hey, I got some current running through because I've got a flow of electrons. And so the flow of electrons off of this metal surface to this other terminal in the tube gives you a signal. Now if we look at what was going on here, it turned out that, well, people thought originally that the intensity of the light is what would cause those electrons to come flying off of the metal. That really wasn't what happened at all. Instead, what it was is that the electrons coming off were dependent on the frequency of light. And so here we see a nice little graph that indicates that. So here we have two samples of light being shown on a metal sample, and even at a lower intensity, which is the red here, comes across, and then at some frequency, the electron ejection rate goes way up. And even at a higher light intensity, here in blue, it comes up and it takes the exact same frequency to come off. Even though the light was brighter, it still required the exact same frequency to cause electrons to come off. Well, this indicated that the intensity of the light is not what was important to the metals, and that the frequency is really what controlled the energy of the light, not the amount of light, but the frequency of the light. So this led to the photoelectric effect. And so Einstein realized that light energy must come in packets with a certain energy, and that energy is dictated by the frequency. So this is what we were talking about earlier. So we came up with an equation where E is equal to h nu, and h is equal to Planck's constant. And it has a very small number. H is equal to 6.626 times 10 to the minus 34 joule seconds. And we'll see that a little bit later in the chapter as we start to get into calculations with this. So here we see that energy is directly related to the frequency, and h is a constant. So by that equation, we can see that as frequency goes up, energy also goes up. Now we can expand this equation by replacing our frequency variable there, nu, with c over lambda, from c is equal to lambda times nu. So what we also have is that E is equal to hc over lambda. What that equation tells us is that energy is also related to the wavelength. And since wavelength is in the denominator, as wavelength goes down, energy goes up. And that would make sense. If we look at energy of red light with a long wavelength, the energy of blue light with a short wavelength, blue light has a much higher energy than the red light. It has a shorter wavelength and a higher frequency. Well, that finishes out Lecture 6. I hope you enjoyed the topics on here, and if you have any questions, make sure you contact us.